Welcome to this video. We're going to be dealing with the second question or the second problem of the first example sheet of MATH2375. So here is the question that we have here. So for each of the following cases, and we give you three sets of functions here, calculate first the Wronskian and then calculate for an arbitrary function y, calculate the 3×3 Wronskian here, and then write down the differential equation which results from cancelling this Wronskian, and then verifying that the functions that we've provided are solution of these equations. Okay, let's get started. So the first case is we give you y1 equals e to the x and y2 equals e to the minus 5x. So first of all, we need to calculate the Wronskian. So the Wronskian is defined as this: y1, y2, y1 prime, y2 prime. And so we just write down e to the x, whose derivative is also e to the x. And for y2, we get e to the minus 5x and minus 5 e to the minus 5x, which is its derivative. And so calculating the determinant of this matrix comes down to calculating this exponential of x times minus 5 e to the minus 5x minus e to the minus 5x. So in other words, the Wronskian is equal to minus 6 e to the minus 4x. Okay, now we're good. Then we need to calculate the Wronskian associated with y1, y2, and y for any function y. So we can write this down as a matrix, which is as the determinant of y1, y2, y, y1 prime, y2 prime, y prime, and then y1 double prime, y2 double prime, y double prime. And calculating this Wronskian may lead to a calculation that is a little bit complicated. What I'd like to do here is to focus my attention on this unknown function, which is y. And so to calculate the Wronskian, there is a couple of possibilities here. What I'd like to do is to transpose the matrix, which gives me the same determinant. So by transposing, I'm getting y1, I'm getting y1 prime, y1 double prime, then I'm getting y2, y2 prime, y2 double prime, and then I'm getting y prime, y double prime. So that's my transposition. After this, I'd like to have my y on the top row. To do this, I need to make a permutation, and the permutation is going to give me a negative sign. So I'm doing a permutation between these two rows, which is going to give me y on the top row, y2 on the second, and y1 on the third. And so then what I'm going to do is a permutation between these two rows so that I have y on the top row, y1 on the second, and y2 on the third. Two permutations, that's two minus signs, which means that I'm going to have essentially the same determinant at the end. So this is also equivalent to the following determinant, which is y prime, y double prime, y1, y1 prime, y1 double prime, and then y2 prime, y2 double prime. Okay, and now we can calculate. So this is going to give me y factor of y1 prime, y2 double prime, minus y2 prime, y1 double prime. Then I've got minus y prime times y1, it's a 1, times y1, y2 double prime minus y2, y1 double prime, and plus y double prime times y1, y2 prime minus y2, y1 prime. Okay, so this is a Wronskian associated with these three quantities. So what we want to look at here is try and make sense of these terms here. In particular, what we can identify immediately is that this term here is nothing else but the Wronskian of y1, y2. Okay, so that's immediate. You should be seeing this very, very quickly, very immediately. And then similarly, what we should identify here is that this is the Wronskian associated with y1 prime and y2 prime. Okay, so we get these two terms already identified. The third term here is a little bit more complicated, but if you see that there's a second derivative, maybe what we can look at is second derivative of y2 here and y1 here. What we can look at is what the Wronskian of y1, y2 differentiated would be equal to. So let's have a look. So the Wronskian of y1, y2, if we remember what it is, it's written here. It's y1, y2 prime minus y2, y1 prime differentiated. And so if I differentiate this, I get y1 prime, y2 prime plus y1, y2 double prime minus y2 prime, y1 prime minus y2, y1 double prime. And the key thing to notice here is that these cross derivatives, they're essentially cancelling out each other. And we get y1, y2 double prime minus y2, y1 double prime, which is exactly the term that we had here. So this is actually the differentiated Wronskian of y1, y2. Okay, so that's key. And you could have noticed it because of the presence of this minus sign and the fact that the second derivative is playing against the function, non-differentiated function. So, in other words, what we've written down here is that our Wronskian of these three functions, y1, y2, y, is equal to the Wronskian of y1 prime, y2 prime, times y, that unknown function that we're interested in, minus the Wronskian prime of y1, y2 times y prime, and then plus the Wronskian of y1, y2, y double prime. Okay? And what we're going to be looking at now is to calculate several equations, several ordinary differential equations that satisfy the equality that this Wronskian is equal to 0. So what we're going to be interested in setting now is w y1 y2 y equals 0. In other words, dividing by this term, this Wronskian, we don't necessarily want this Wronskian to be equal to 0, which would mean that there are some special points where the theory that we like to apply for second order differential equations doesn't apply. Then by dividing by this, we end up having an equation that writes like this: y double prime minus w prime y1 y2 divided by w y1 y2 plus w of y1 prime y2 prime divided by w y1 y2. And I forgot the y's, apologies for this. This is y prime times y equals 0. And so what we see here is that we have managed to write down our equation in the usual form for a second order differential equation, homogeneous and linear, which is that we've written down y double prime plus p of x, y prime plus q of x, y equals 0, where p of x equals minus w prime of y1, y2 over w y1, y2, and q of x equals w y1 prime, y2 prime divided by w y1, y2. Okay? And so back to our original. So now we've essentially derived this these equalities here. Now back to our original problem where we had these two functions, that was a long time ago, y1 and y2, which is exponential of x and exponential of minus 5x. Okay, so we need to find the equation that satisfies the Wronskian y1, y2, and y equals 0. So what we essentially need to determine here is the value of p and q. So p is equal to minus the Wronskian prime y1, y2 divided by the Wronskian y1, y2, sorry. So that's minus, and my Wronskian here was minus 6e to the minus 4x, if I remember well. Let me just check that quickly. Yes, that's correct. So that is my Wronskian. So I'm taking the derivative of this and I'm putting this into onto the numerator, and that's 24e to the minus 4x. And so in other words, not forgetting this minus sign here, my p of x here is just equal to 4. It's a very simple value. Okay. Now we need to calculate the Wronskian we need to calculate q of x. So let's go ahead. Q of x. And q of x is the Wronskian of the derivatives of our functions divided by your usual Wronskian. Okay. So here what we have is something in the numerator that looks complicated, but let's just write down the denominator first. And to look at the numerator, there's a trick. So our functions, if you remember well, they're y1 equals e to the x, leading to y1 prime equals e to the x, leading to y1 double prime is e to the x, right? And y2 was e to the minus 5x, which leads to y2 prime equals minus 5e to the minus 5x, and y2 double prime is 25e to the minus 5x. And you can keep going like this. Try to calculate the Wronskian of, try to calculate this Wronskian here as a function as opposed to the Wronskian that we calculated originally, which was on the green quantities there. But the key thing to notice here is that one line of the Wronskian is, one column of the Wronskian is going to be comprised of these quantities. That's going to be column 1, and the second one is going to be column 2, comprised of the quantities associated with y2. And the key thing here is that when you go from the Wronskian of y1, y2 to the Wronskian of y1 prime, y2 prime, column 1 stays the same. It's e of x everywhere. But column 2 changes. That guy becomes this guy, which is minus 5 times what it was. And that guy becomes this guy, which is minus 5 times what it was. So essentially, the Wronskian of y1 prime, y2 prime is going to be the same as the Wronskian of y1, y2, except that the second column is multiplied by minus 5. Okay? And as a result, the determinant of that matrix is just minus 5 times what the determinant of the other one was. So based on this reasoning, the Wronskian of y1 prime, y2 prime is minus 5 times the Wronskian of y1, y2. So there's no need to calculate the Wronskian of the prime quantities here. And therefore, I'm just going to scrap this out and write down that immediately the result is minus 5 due to the structure of the functions that we've been applying here. Okay? And so the last part of the question, so now we have this equation. We have the equation that these function, or that results from the Wronskian y1, y2, y equals 0 is y double prime plus 4y prime minus 5y equals 0. And the last part of the question was to ask you to verify that our two functions are solution of this equation. So let's check y1 equals e to the x. The key thing to notice here is that y1 prime is e to the x, which is also y1, and that y1 double prime is also going to be y1. So what we have is that when we replace in our original equation minus 5y1, when we replace here, we get y1 plus 4y1 minus 5y1, and that is equal to 0, which is the right-hand side, and I'm going to call this equation 1, of equation 1. Okay? And so y1 is a solution of 1. Okay, the second function that we need to check is y2 equals e to the minus 5x. And in a similar vein as before, we can just essentially write down that y2 prime is minus 5y1, and that y2 double prime is 25y1. No, y1, sorry, y2. And so using these, we can write down that y2 double prime plus 4y2 prime minus 5y2 equals, so the double prime is 25y2 minus, plus 4 times the prime, so that's minus 20 y2 and minus 5y2. And that is equal to 0, which is what we were looking for. So this is, which is the right-hand side of equation 1. So y2 is a solution of 1. Okay, so that was the first set of functions that we gave you. Then there is a second set of function that we gave you, which was, let me fetch this. So it was y1 equals x squared, and y2 equals x to the minus 3. And so once again, we ask you to calculate the Wronskian of these functions. So the Wronskian is y2 here is going to be y1 prime, y2 prime, which is x squared 2x, x to the minus 3, and minus 3x to the minus 4. Calculating the determinant of this matrix, we get minus 3x to the minus 2, minus 2x to the minus 2, which is minus 5x to the minus 2. Okay? And then, in the same vein as before, we ask you to calculate the equation that results from setting y1, y2, y equals 0. And so using the same result that we've demonstrated earlier, we get an equation that should be like this, that should write like this. And we get q of x, y equals 0, with p of x equals p of x equals minus w prime of y1, y2 over w y1, y2, and q of x equals w of y1 prime, y2 prime divided by w y1, y2. And I strongly emphasize here that this looks like complicated material to remember, to learn, but in fact it isn't. If you do this calculation, sorry, my tablet is saving. If you do this calculation that I've done about this determinant here, this big determinant, this 3×3 determinant here, if you do it a couple of times, then redemonstrating this is relatively simple. It takes a bit of time to write this calculation, but it's relatively simple, and I guarantee you that you'll learn, just by doing the calculation, you learn the structure of this equation, and these terms would then come, P and Q would then come to you without having to memorize them. Okay, So let's do this. So p of x, then here for our function, remember that our Wronskian here is written minus 5x to the minus 2. So p of x is minus w prime, so that's 10x to the minus 3 divided by the Wronskian, which is 5x to the minus 2. And so what we get here is we get 2 divided by x. So that's our p of x. And our q of x is going to be more complicated as usual because of the presence of our Wronskian of differentiated quantities. So y1, y2, and so we need to calculate this secondary Wronskian first. So Wronskian y1 prime, y2 prime is, so y1 prime was 2x, and so the second derivative is going to be 2, and y2 prime was minus 3x to the minus 4. So the second derivative is going to be 12x to the minus 5. Going on with this calculation, our Wronskian then becomes 24x to the minus 4 plus 6x to the minus 4, which is 30x to the minus 4. Okay, so that's our Wronskian of prime quantities. So what we get here is 30x to the minus 4 divided by our usual Wronskian, which is minus 5x to the minus 2. And so the result is minus 6x to the minus 2. Okay? And so what we get here, the final equation that we get in this second problem is y double prime plus p of x, which is 2 over x y prime. Then we get plus q of x, which is minus 6 over x squared, y equals 0. And we can rewrite this in a potentially nicer way. Don't necessarily like to have denominators, fractions in these equations. So I can multiply everything by x squared and get x squared y double prime plus 2x y prime minus 6y equals 0. And that's going to be the equation that we'll be working with. Okay, so we need to verify now that our two solutions, or two functions, are solutions of this equation. So the first one that we want to check is it's x squared, y1 equals x squared. So we get y1 prime is 2x and y1 double prime is 2. So plugging this into our equation, and I'm going to call this equation 2. So we get x squared times y1 double prime plus 2x times y1 prime minus 6y1. That's equal to 2x squared. Then we have plus 4x squared, and then we have minus 6x squared, and that's obviously 0, which is the right-hand side of equation 2. So what we get here is that y1 is a solution of 2. Okay, that's one done. And then now we need to check y2. And y2 was x to the minus 3, which gives us y2 prime is minus 3x to the minus 4. And y2 double prime is 12x to the minus 5. So if I plug y2 in my equation, I get y2 double prime plus 2x y2 prime minus 6 y2, and that's equal to, so the first term is multiplied by x squared, so I get 12x to the minus 3 plus 2x times, there's going to be a minus sign here, so plus 2x, so that's minus 6x to the minus 3, and minus 6 x to the minus 3. And that's also 0, which is the right-hand side of equation 2. And therefore, what we have here is that y2 is a solution of equation 2. Okay? And given the length of that video, I'm going to leave the third example to you, which is more or less a combination of the first two, to your discretion.